Okay, our fourth and final intro to science video has to do with just some different scientific principles. The first of which is accuracy versus precision. A lot of people use them interchangeably, but they're not. They actually mean something very specific. For instance, accuracy is how close you are to an actual goal or target. So if you're thinking about here on the bullseye, something with a high amount of accuracy would be something that hits close to your bullseye point, right? Now, precision doesn't necessarily have to do with getting that to the goal. It's how close every shot or every dart in this case would be to each other. So you get very high precision if you get them grouped all together. Now, you can fail and get them neither. So this is low accuracy and low precision because, as you can see, they don't really get close to the bullseye, even though they do hit it once. The vast majority of the time, they hit way off of it, and none of them are grouped well together. That's considered very poor by anybody's standards. Now, the next one up, we try to get things that are high precision. So notice that this is really good because everything that we're shooting is getting on the same point, but it's still a good far ways from an accurate point. So though we are calibrating it to the right place, we're still not getting it to where we want overall. And then again, you can also have the counter of that, which is high accuracy, where we're all hitting around there, but they're still spread out pretty much. So we do get close to the goal that we're looking for, but we don't quite get it there every time. That's low precision, but high accuracy. And then, of course, we have the goal of all science, to be both accurate and precise. High accuracy, high precision means that you're hitting your goal almost every time. So hitting the bullseye. And that's what we're going for in science. This is just your basic scientific method. Most of you have probably seen it somewhere in your life before now. And most people think about the scientific method pretty much how this diagram shows it, in a linear path. Even though I do know this one has a couple of roundabouts here and here, because it actually was done from a better site, it still looks like that idea that someone thinks back in, I don't know, about third grade. I ask a question, I do research, I come up with a hypothesis, I test the hypothesis, I do my work procedure, and then I get data and it gets some sort of result. And I say, hey, look, I'm smart, I have scienced. The truth of the matter is, this isn't really what science looks like, but it does hit on some good points that you do have to ask questions, you do have to research, you do hypothesize, that's taking a guess. And then there is experimentation that goes through different procedures, but notice that it does loop back around a good bit. Then you're going to have some sort of data that you can analyze, hopefully draw some sort of conclusion. It doesn't necessarily have to back up your hypothesis, it just has to be related to. If it's not even close to your hypothesis, you probably want to go back and create a new hypothesis, which will cause you to set up a new experiment and go all about until you have something that you can say may or may not affect it. Again, it's not a definite. This is a much more accurate look at what science looks like, because every question, every conclusion leads to another question. And so if you really think about the scientific method, you should think about things in a rotating circular fashion, like we see right here. So notice that in this one, you can start at any point. It might have been a theory that was developed by somebody else, but at the same time, you might be making some sort of observation in nature. A lot of times that's where people think about starting because they think, I have that. But here's the thing. You then need to try to think of some interesting questions of why you're making these observations. You're also going to have to do some research to figure out what was done beforehand. Then you're going to come up with some sort of hypothesis, your guess, right? And you develop these tests to test your hypothesis. You will gather data from a test, whether good or bad. That might just mean that you need to reevaluate your whole testing procedure, create another way to test it, and keep doing that until you get something that you think is a good idea that you'll develop into a theory. Notice they're theories, they're not scientific facts, because you don't prove things. You can disprove things, but you don't prove something for certain. You just come up with things that is the best guess at the time, but that leads to other people making other observations and starting the whole process over again. People have it in their mind that they're going to do a scientific experiment and they're going to find something, and then it's hardcore fact that no one can argue with. That's not the purpose of science. The purpose of science is constantly to question, constantly to refine, constantly to come up with better testing, better ideas of things that we can get consistent results in that other people can repeat. Doing that means we have to follow a certain type of procedure when we're doing scientific methods. Now, while the scientific procedure of real science involves a whole lot of different things, the three that we're really going to look at are these: controls and variables. That's controls, independent variables, and dependent variables. This also gives you an idea of what is good science and bad science. Because if you're testing a particular aspect of something, you're going to need a good amount of controls. And so many times in science in the past, they've done experiments where they didn't have a good amount of controls. There's a very famous scientific experiment that supposedly proved spontaneous life. What they did is they put some meat out in the desert and they watched to see if maggots ever crawled on it. They never saw maggots crawl on it, but then suddenly maggots started to appear. The problem is they didn't control what else went onto it. For instance, flies. Flies are basically maggots. The maggots are the larva form of a fly. So when someone finally had a better control to put the meat in some sort of jar, they no longer got maggots, and they disproved the previous theory. Controls are the things you keep the same. You're not changing those. You're trying to keep everything exactly the same so that other things don't interfere with your results. Controls are the things you're locking down. Think about it that way. All right, then that leads us to our independent variable. Our independent variable is the one that you actually do want to change. So if I thought, let's say that I'm growing corn, right? And I want to find out what fertilizer makes it grow the best. Well, there's a lot of things I have to control to keep the same. I'm going to control the amount of water that it gets, the amount of sunlight that it gets, the amount of wind blowing on it, the amount of space it has to grow. I'm going to make sure all of that stuff is the same if I'm trying to control the amount of fertilizer or the type of fertilizer that it needs. Then I would change that type of fertilizer. That would be my independent variable. It's the thing I'm actually changing, hoping that I'm going to get some sort of different result. So let's say I use pig manure as a fertilizer in 1, I use chicken manure as a fertilizer in 2, I used an artificial made nitrate for a fertilizer in 3. It's changing for every one of my experiments. It's the independent variable. I'm changing it on purpose while keeping everything else exactly the same in order to see how it affects things. But then I need to be able to measure that somehow. To measure that is where I need my dependent variable. My dependent variable is simply my tool of measuring my results and my success. So if I'm doing something like corn, you might think that I would measure maybe how many ears of corn. Then my dependent variable is a simple count of how many ears of corn I get. But I might be measuring the height of the plant. then I'm using some sort of length measurement like meters. How many meters did it grow? Or I could be measuring how healthy the plant looks, so a mass. And really, you can have multiple dependent variables. I might be looking at a factor of how big it got, how much mass it had, and how many ears of corn that it developed. But the dependent variable is dependent on the success or failure of the experiment. So it's the measuring tool that you use in your experiment. It depends on something else, right? Okay, now I hope you understand those, because you're now going to watch a video and you're going to do an assignment where you have to identify controls, independent variables, and dependent variables. Hope that helps.